Okay, so remember, intro to basic stats. So I'm gonna teach you guys like the basic definitions and stuff. You guys should know most of this stuff, except for maybe like stuff at the end. So here we go. Let's get started. All right, so basic vocab. So you guys know mean, median, mode, range, probability, and chance. Chance is a little different. I'll explain it later. So you guys know that. So if you don't know, mean, also known as the average, is the sum of all your data. I pronounce the data. You can pronounce the data. Divided by the n amount of data you have. And it can also be decimal. It can be a fraction or a decimal. Most people actually like using decimals for stats. That's crazy, you know? So for example, if you had a list of salaries from 3 different people, the average or the mean would be all 3 salaries added together, and then you divide it by 3 because you have 3 different people. Just a quick example. So if you had someone's made $1, someone made $2, and someone made $3, you just add them all up. 1 plus 2 plus 3 is 6 divided by 3. So your mean would be 2. So the average salary from these 3 people is $2. That's just basically what I mean. All right, median. In a list of data order from least to greatest, or you could do greatest to least. It doesn't make a difference, but you have to order it though. If the list of data is unorganized in that order, either greatest to least or least to greatest, you can't find the median that way. So anyways, so in a list of data ordered from least to greatest or greatest to least, the median is the number in the exact middle of the list. And it can also be a decimal because sometimes you can have 4 numbers, 1, 2, 3. If you have an even number, your median will be the average of the 2 numbers in the middle. So 1, 2, 3, 4 is least to greatest. And what you do is you just start by canceling the numbers, the same amount of numbers on each side until you reach the center. What is salaries? Salaries is your income. It's how much money you make. That's a salary. Annual salary means a yearly income. How much money you make in a year. Monthly salary, how much money you make in a month. Daily salary, no one has daily salary because unless you're like odd jobs or something, because people get paid every month or so. Yeah, that's how paychecks work in the modern world, guys. At least that's why I think it is, because if you're getting paid daily, either you have a really good job or something's a little shady. That's a little illegal. Get paid daily. Anyways, so like I said, so if you had an even amount of numbers, the median would be the average of the 2 middle numbers. So in this case, the median, there's no, you can't, because there's no number in between 2 and 3. But if you take the average of 2 and 3, which is 2 plus 3 divided by 2, you get 2.5. So that would be your median in this list of 1, 2, 3, 4. That's a median. So for example, this list has 5 numbers, so you can have a good median. The median would be 3 because you have to order it. So 1, 3, 2, 6, 7. I do, at least personally, I learned least to greatest growing up. You could do greatest to least. Doesn't matter. So if you order it from least to greatest, you'd be 1, 2, 3, 6, and 7. And you start canceling numbers from each side, one at a time, and you'll end up with 3 in the center. That's a 3. So the median would be 3. And mode. So in a list of data, the mode is the number that appears the most frequently. If there is no mode, I think you say no mode, because sometimes there's like 1, 2, 3, 4, 5, 6. Like you have 1, 2, 3, 4. There's no mode in this one because each of them appears once. I think you'd say no mode. I've never seen a question like that because mode is probably the least relevant statistical element that you ever learn. People only care about the mean and the median in the real world. No one cares about the mode. I'm sorry, mode. But yeah, I think you say no mode because you don't want to say like 1, 2, 3, and 4 are all the modes. That defeats the purpose of the mode. But yeah, like I said, a mode in a list of data is the number that appears the most frequently. So in this case, the list of 1, 3, 2, 2, 51, 6, and 7, because 2 appears twice and everything appears once, 2 would be your mode because it appears the most in this list. All right, continue. So the range, you guys know range. The range of a data set is the highest value of the set minus the lowest value. So for example, in the previous list we had, the 1, 3, 2, 2, 51, 6, 7, the range would be 51 minus 1 because 51 is the greatest value and 1's the lowest value. So 51 minus 1 is 50. So 50 would be your range. I guess if there is no like highest value, I think you just still subtract that and that. So you, like the range would be 0 if there's no highest value and they're all the same. That doesn't give you much statistical data though. So at that point, the range would be irrelevant. So don't question, like don't try to find the range if there's no lowest and highest, or if they're all the same numbers. Because if you think about it, that's the range is 0. Like that only tells you they're all the same, but then there's no statistical variability and no statistical significance, no good p-value found in your data. So either your experiment is flawed or it's a really good coincidence, just a really, really, really good coincidence that they're all the same. That's how stats, welcome to stats, guys. I don't even know stats that well. I know p-values. I know, that's not standard deviation. Standard deviation, that's not it. I know chi-square tests. Welcome to stats. I don't even know that much of stats. I know stem leaf plots, dot plots, histograms, discrete concrete variables. Yeah, okay, it's advanced stuff. Don't worry. All right, probability. All right, you guys know probability. So it's the likelihood of an event occurring within a data set or a set of conditions. Box and whisper plots. Oh, whisker plots, yeah. You're not gonna learn that today. Well, I didn't include it in my lesson, this lesson, but I never personally learned box plots. I probably should have. Sorry, I'm drinking water. I probably should have, but I never learned it because that isn't my field of study that I'm planning. Okay, so probability, the likelihood of an event occurring within a data set or set of conditions. And it's usually a fraction, always a fraction. So for example, probability of drawing an ace of spades from a standard deck of 52 playing cards. If you guys don't know, like those playing cards, you guys, I don't know, have you guys seen playing cards? 52, because it's 2 jokers, 50 cards. So the probability of drawing one ace of spades, because there's only one of that certain card in the deck of 52, is 1 out of 52, which is a pretty low chance. If you turn that into a decimal, that is approximately a 2% chance. And notice I said chance, not probability. So the probability is 1 out of 52. It's a 2% chance. That's different because chance is the same thing as probability, right? Not really. Yes, but actually no. That's an old meme, by the way. I'm cringy. Okay. Yes, but no. So the main difference is that chance is always said as a percentage. Like I said, I talked to my teachers about this, and they're like, "Yeah, this is people. A lot of people get it mixed up." Obviously, chance is more used in the real world because it's more practical. But the specific nitty-gritty details of it, probability is defined as P of X is equal to, it's the ratio of odds. So it's equal to chances for the event divided by the chances total. So it's actually a ratio. It's a ratio between the chances of actually getting, like achieving the event of what you want, and then out of the total chances that it's possible, that like the different possibilities you can get. And chance is more like a prediction or a forecast in practical terms. So in everyday terms, we say like, hey, it's gonna be a 50% chance to rain. So it means it's a 50-50, you know, it's not gonna, it might rain, it might not rain. Honestly, usually when they say that, it's probably gonna rain anyway. So there you go figure. So for example, if you flip a coin rolling heads, it has a probability of 1/2 or 1-to-1 odds because there's 1 heads, 1 tails. So it's a 1-to-1. Or there's a 50% chance to roll heads. Now, obviously, I'm not gonna like nail you down. I don't even nail people down that don't use it correctly, but technically, like mathematicians, the super high ones, so like that PhDs and all that stuff, they're like, oh my God, like all these guys are talking chance and probability, like it's interchangeable and all that. Yeah, don't worry about that. Just a little cool thing to know, especially this P of X thing, because a lot of people like to use functions a lot. All right, practice. So use this list of data to find the mean, mode, range, and median. And then question 2, find the probability of drawing a queen from a deck of 52 cards. There are 4 queens, by the way. There's 4 different queens. 1 for each soup. And then use this one to answer the next 2 questions. So in a bag of 14 total fruit, there's 6 apples and 8 oranges. Use this info to answer the next 2 problems. All right, problem 1. Find the probability of taking out an apple or an orange from the bag. Find the probability of taking a pear out from the bag. And the challenge problem, find the probability of one person not taking out an apple, then putting it back in the bag, then another person coming in, taking out an orange and putting that in the bag. So basically 2 different events from 2 different people. So I'll give you guys a little bit to do that. Should be really easy, really simple. The last one is the challenge problem. You probably don't know how to do it. I'll tell you guys how to do it later. Let's see, I'll order this list. Least to greatest. Let's see. So if I order this from least to greatest, start with 1, 3, 4. So take this out. 1, 3, 4, 5. Sorry about that. 2 5s. Jeez, sorry. Hold on. What does mode, range, and mean mean again? So mode is the number that appears most. Range is the highest number minus the lowest number. And mean is the average. It's another word for the average. 1, 3, 4, 5, 6, 6, 7, 8, 10. There you go. So if I ordered this from least to greatest, that should help you out for median and range. I actually visualize the range really well too. Find a probability. Okay, you guys should do this one, be able to do this one. Oh yeah, you can have multiple modes. Yeah, good catch there.
What was the mode again?
Mode is the number that appears the most in your list.
Oh, thank you.
Yep. You guys getting the same median as, or sorry, mean as me? You guys are getting different means. Different averages. Remember, average is you add it all up and then divide it by how many numbers you have. So in this case, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. And you add up 1 plus 3 plus 4 plus 5 plus 5 plus 6 plus 6 plus 7 plus 8 plus 10, then divide all by 10. How do you not take out an apple, but then you can still put it back in? Well, think about it. So probability of not taking out an apple is the same thing as the probability of taking out an orange, because there's only apples and oranges. You not taking out an apple is the same thing as taking an orange out, because there's nothing else to take out. So that's basically what I mean by that. It's a little, that's a trick question, a little trick question. You're close, Zoe, to the mean. Close, close. So if I add all this up, 1 plus 3 is 4. So 1 plus 3 plus 4 plus 5. Just write this all out. All divided by 10. All right, so 1 plus 3 is 4. 4 plus 5 is 9. 5 plus 6 is 11. 6 plus 7 is 13. It's 18. 4 plus 9 is 13. Plus 11 is 24. Plus 13 is 33. Plus 18 is 55. So it's all 55. Divide by 10. And it's 5.5. So your mean is 5.5. I think their median is also 5.5. Because if you cancel, whoops. If you cancel out these numbers, so cancel out the, Jesus. Give me 1 second. All right, cancel out the 1, cancel out the 10, cancel out the 3, the 8. And then wait till you get there. So 5 and 6. The average of 5 and 6 is 11/2, which is 5.5. So your mean and median are 5.5. They can be the same. Your mode is 5 and 6 because they both appear twice in the list. And your range is 10 minus 1, which is 9. So 9 equals range, RNG, sure. 5, 6 equals mode. There you go. All right. This one is just simply 4 out of 52, which you can simplify to, I believe, 1 out of 13. If I'm not mistaken. Yeah, 1 out of 13. This one, so 6 apples, 8 oranges. Probability of taking out an apple or an orange from the bag is 14 out of 14, which equals 1. So you have a 100% chance or a 1 probability of 1 taking out an apple or an orange because there's only apples or oranges. Right? Probably taking out a pear from the bag is 0 out of 14 because there are no pears in the bag. So it's not possible to get a pear unless you're a magician, which I hope you guys aren't because that's kind of creepy if you get a pear. Actually, that'd be pretty cool, actually. And this one, so challenge problem, I explained in the next slide, but basically, when you have 2 different events independent of each other, you multiply the probability of each event. So this one is the probability of a person not taking out an apple, which is the same thing as probability of taking out an orange. So 8 out of 14 times another person taking out an orange and putting that back in the bag. Also another 8 out of 14. Because they both independently have an 8 out of 14 probability to take out an orange in this bag. And since they're independent from each other, what I mean by that is like their results don't influence one another, right? Because if someone takes out the fruit and then just puts it back in and leaves it, that shouldn't affect what the next person will take out. Even if it was the same person, that shouldn't affect it because, unless he knew, he was purposely going for it. So 814 times 8 over 14, 814 squared. So yeah. So basically those are your answers. Come on. Okay, so like I said, 5.5 is your mean, 5 and 6 are your modes, your median is 5.5, the range is 9, because 10 minus 1. Probability of drawing a queen from a deck, because there's 4 queens in 52, so it's a 4 out of 52 probability. And if you simplify it, it's 1 out of 13. Yeah, those are right, Zoe. Yep. 13%, I don't know about that one. I don't think so. Let me check. Yeah, there's no way. Yeah, that's an 8% to get a queen. And then, like I said, probability of taking an apple or an orange is 1 because both. It's or. If you have or, you always add. If you have and, you multiply, but that's advanced stuff. Pair is 0 because there's no pairs. And like I said, you multiply. So it's a 16 out of 49 probability because you do 8 over 14 squared. Which, yeah, you can simplify this fraction inside first and then just square it. 4 times 4 is 16. 7 times 7 is 49. And you can no longer simplify this. So, yeah. I think you guys got the hang of this, right? 90% sure you guys learned this already. This is like basic stats, except for this last problem. This last problem is technically not basic. All right. Frequency tables and dot plots. So you can graph stats, and we're going to do that today. So frequency tables and dot plots are just some of the many ways we can represent collected data. Frequency tables tell you how many times, or the frequency, that's a definition of frequency, a certain data value shows up. And dot plots take the frequency tables and represents its data or values visually to help you see, how much of it is spread out or the distribution of data. So dot plots help you see the distribution of data, how it's spread out throughout the the entire graph. Dot plots can also be made from other tables too, or a list of data. You don't have to be from a frequency table. It just helps if you make a frequency table to get you organized and see it a lot better. So yeah. Obviously, you got to get your units right because, for example, if you had a list of test scores from different students, your units would be the test scores on one column. So it'd be like 2 columns like this, like a T-chart. Usually the left column has like your units, so test scores here, tests, and then the like percent, right? Because then the frequency of the scores on the other column. So like percentages, frequencies, numbers, amount on the right side, the test scores on the left. Likewise, if you had something like, I don't know, if you had a bunch of cars and you're trying to compare speeds and given amount of time or something, you'd be like, on the left would be car model, on the right would be max speed or something. And then, yeah, it would be like, hey, if 2 cars went 50 miles per hour, then you'd be 2 right here, it'd be 50. And another one did like 45, 3, stuff like that. So here's an example. So here's a list of test scores I made up when I made this last night. I made this slide last night, by the way. And so basically, I list the test scores out and I see that there's 1, 2, 3, 4, 5, 6 different numbers of test scores, different numbers, because some repeat. So there's 6 different ones. And then number of scores is I just basically see how many times it appears in the list, the certain number, a certain test score, and see how many times it appears in the list, and I just put down the frequency, put down how much. So for example, so I seen a list for 79. There are 1, 2, 3 79s. So the frequency would be 3. Likewise, there's only 181 in this entire list. There are 482s, 1, 2, 3, 4, 482s, and so on and so forth. So basically, you just organize your list in this frequency table. And it can get pretty tedious if you have a really long list, which is why we have like algorithms and AI and coding to do all that these days, because it's super tedious by hand. But yeah, in a small list, this isn't that big of a deal. Okay, so an example of a dot plot using a frequency table. So create a dot plot using the same list, sorry. So here's the table again. And so dot plot is basically, I just take whatever units or whatever numbers is on the column, and I just put it in, and I just space them out real nicely. And then I see, okay, 79 has 3. So I'm gonna add 3 dots or 3 X's. I did X's in this one. I'm gonna add 3 whatevers. You can do dots like that, 1, 2, 3. I don't know if you can see that well, but you can do like 3 circles, 3 squares, anything that can easily tell you, you know, how many, the amount of test scores or whatever you're comparing. So there's 3 test scores here. So I put 3 X's, 1, 2, 3. Likewise, there's 181%. There's 482%. There's 283%. There are 495%, and there's 199%. So yeah, you can see it's pretty, the distribution data is more towards the right side. We call this left skewed, or skewed to the left. But there's a little bit of outliers on the 79, just a little bit. But yeah, you can see, so you can easily see, you know, which score has a lot of and which score has a little. The mean test score is 86.5. Oh, let's check that. I wouldn't know. I'm not looking for that, but hey. Let's see. We check that real fast. I got 86.06. I missed a number. 82, 95, 95. Let's go backwards. 99, 82, 82. I got 86.066. I'm repeating. But yeah, you're close. 86.5. Good job. At least you know the general process. You just add them all up. You add 79 plus 79 plus 81. and so on and so forth until you get to 82. And then you divide by how many test scores you have. So in this case, you would have 4, 6, 5, 15. You have 15 test scores. That's a 5. You would have 15 test scores. So divide by 15. But I hope you guys see that. This is pretty simple. You just take your frequency table and put whatever amount is on the right side and just put it in. And like I said, you don't have to use X's. You can use dots. It's called dot plot for a reason. You can use dots. You can use shapes, triangles, squares, circle. I don't know. I just did X's. All right, histograms. So a histogram is another way to represent data, also from a frequency table. And you might have seen histograms as a bar chart or a bar graph. So it looks something like this, right? This is a histogram, something like that. It's called a histogram. They do differ. Bar graphs / bar charts are a little bit different. But you don't need to know about that because I think bar graphs have discrete variables or something. Don't worry about it. I never learned this advanced stats too. Don't worry about it. All right, so the process of creating histogram is also pretty simple. So first you want to find out what units to put in the y and x axis. No, the frequency always goes in the y axis. Just a note. Then you want to label your graph and make sure you title it. You have to title your graph, okay? If you're doing a science project, anything, a math test, make sure you title your graph. That's very important. And people are nitpicky on that because then if you don't title your graph, you're like, what am I looking at? I'm just looking at bars. If you don't title your graph, they don't know what you're looking at. Then find out the class width or just the interval on the x-axis. So for example, like if I had a bar graph, put like 0 right here, then 10 right here, and then 20, the class width would be 10, right? Or 9 technically, because 0 to 9, and then 10 to 19. So the class width would be 9, or the interval. So you just want to see how much you want to space out your x-axis based on the list of data you have, what's reasonable. And then you just graph the bars based on the frequency. So obviously the higher the frequency, the higher the bar, the lower the frequency, the lower the bar. There you go. So an example. So let's say you surveyed students on how many minutes they spend on homework each night, and you got this list. So somebody spends 6 minutes of on homework a night. That's a stellar student right there. 6 minutes a night. Dang, I wish I could do that. Okay, so you got this list, pretty big, right? And you look at this, it's probably make the most sense to create your frequency with the intervals of 9 minutes, starting at 0 minutes, because you want to count by tens. So you get like 0 to 9, 10 to 19, 20 to 29, count by tens basically, but the interval length is 9. A little confusing, I know, but it'll make sense. So here is your frequency table. So you have 0 to 9, 10 to 19, 20 to 29, 30 to 39, 48 to 49. And then the next one would be like 50, if you keep going, 50 to 59, and so on and so forth. So how I determine the frequency is obviously from the list. I'm gonna spend 5 minutes as well. I put 5 here. I made this, by the way. How would you determine this? The frequency is just look at the number and see if it falls in the interval. So 5 and 6 fall in between 0 to 9. So you have 2, and that's it, only 5 and 6, and so on and so forth. 10 to 19, you have 17, 12, 18, 19. Those 4 fall within this interval, 10 to 19. So you have 4. So pretty simple. Like I said, really tedious. If you had a longer list, like a super duper long list, really tedious. That's why we have robots and AI these days. But everything we had to do by hand. All right, so now we create histograms, and I'm kind of repeating a few points, but like I said, it's pretty important. So the y-axis always be frequency, and the x-axis will always be your intervals of whatever units you choose. So in this case, would be minutes. So your x-axis would be spaced out 0 to 9. Make sure you label your graph and title it. Like I said, very important, because you don't know what you're looking at if you don't title it, like I said. And then use the frequency table to determine how tall each bar of the histogram will be. So you go, here's your frequency table, and I magically created a histogram. Now this isn't exactly right, technically. because the numbers appears in the center of the bar. But this is roughly what it looks like, because notice you get the 0 to 9 has a 2 right here. The 10 to 19 is 4. 20 to 29, which is basically 20 to 30, has a 2. And then this is the tallest. The 30 to 39 has a 7. And 40 to 49 is 4. If you really wanted to be like really clean, I guess you would like this. So like 0, 10, 20, 30, 40. And how it works is that the bars starts at the edge of the number. So this is, let's say this is 2. This is 4, 6, 8. Okay. So you have 0 to 10, and this bar ends at the edge of 10. And then you have 10 to 19, which is 4. So it would look like this. And the bars would be together. They wouldn't be spaced out like this right here. The bars would probably be together. So 10 to 20 have 4. 20 to 29 is another 2. So like that. This is a rough estimate. This is roughly 29. It's on 30, but it's roughly 29. 30 to 39 will have 7. So up here. And I should put 50. I forgot 50. That's okay. And 40 to 49 will have 4. Like so. So that's what a true histogram looks like. The not spaced out, and they're clunked together, and the intervals are close by each other. Like that. Basically a bar graph. Basically. It's no different, honestly, in my opinion. But hey, advanced statisticians, did I pronounce it? They'd be like, oh, they'd be all nitpicky and stuff. So yeah, I'm not too concerned. All right, little practice. So make a frequency chart and a dot plot with this data. So a student creates a list of different tempos, which is like the speed of a song or her beat, of all the songs that are her classmates' favorite songs. She finds that 3 songs have 58 beats per minute. BPM is beats per minute. That's the tempo. 5 songs have 120 beats per minute, and 3 songs are 78 beats per minute, and 2 songs are 90 beats per minute. So make a frequency chart and a dot plot this data. So I'll let you guys do that real quick. And obviously your units would probably be tempo or BPM. How do you make a frequency chart? Okay, well, you'll see. Okay, so your units on the left side would be tempo or BPM. On the right side would be like just frequency. And then, so you have how many different tempos? You have 1 tempo, 2 tempos, 3 tempos. You have 4 different tempos, so 4 different categories. So 58 goes here, 58 BPM. You have 128 BPM, 78 BPM. 120 is pretty fast. Tempo frequency, yeah, and then 90 BPM. That's how I would do it. So you have 90 BPM. And the question told you 3 songs are 58, so the frequency is 3. 5 songs are 120, frequency is 5. 3 songs are 78, frequency is 3. And the 2 songs are 90. So this is your frequency. Frequency is how much it appears if you made a list. That's the definition of frequency. And then you make your dot plot. So you have tempo frequencies, I don't know, label it something. Tempo frequencies, and bottom is tempos. I know my handwriting is really bad, but tempos. So this is tempo frequencies on top as your title, tempos. And so you just basically input these in on the x-axis. Yeah. So you have 58, then 78, because you usually want to go least to greatest to organize it, 90 and 120. And then you just take your frequencies and put whatever symbol you want. You can do dots, circles, triangles, like I said. I'll do X's, make it look easy. So there's 3 songs with 58 beats per minute. So you have 1, 2, 3. There's 3 songs with 78 beats per minute. 1, 2, 3. There are 2 songs with 90 beats per minute. And there's 5 songs with 120. 1, 2, 3, 4, 5. You can't see the last one, but that's it. That's how you do it. That's basically a dot plot. You just take your frequencies and it's equal to the number of symbols you want. And then whatever you have on your left column, you just put on the x-axis. Pretty simple stuff. All right, let's move on. So now this time, make a frequency chart and a histogram with this data. So there's a book that consists of 425 words. A book that consists of 425 words is analyzed. The analyst sees that of the 425 words, 198 are made up of 1 to 3 letters, 205 are made up of 4 to 6 letters, and 22 are made up of 7 to 9 letters. Those are some big words. So make a frequency chart and a histogram. So I'll leave you guys to it. So I'll give you a little hint. Well, not a little hint. I'll get you guys started. Frequency. I guess the left side will be number of words. Actually, no, that's your frequency. Number of letters. That's your left side. Number of letters. And the question clearly sets up your intervals, 1 to 3. You have 4 to 6. So your class width is 2. And 7 to 9. Class width is 2 in this case, or your interval spacing is 2. And so you just input the frequencies and you make a histogram based off that. All right, for the sake of time, let's make a mock one because the next one, I didn't put answers for that because Google Sheets doesn't want to work with me. So let's see, frequency be 198, 205 because 4 to 6 letters, and 22. And you just basically graph it. So you just be like, your title would be something like number of letters versus words, something like that. Numbers of letters with words, like no, amount of words with certain number of letters as your title or something like that. So your whatever title on top, and basically you start at 1 right here, and go to 4, and then go to 7. God, I'm doing this really bad. So basically, you only have 3 bars in this case because there's only 3 different categories. So 1, you go to 4, and then you go to 7, and go to 9. Technically, you have 3 bars, but 4 numbers. So your 1 to 4 be 198. So let's say this is like in 50s. 50, 100, 150, 200. Really bad looking. I know, I'm sorry. Sake of time, we're running out of time, sort of. So 198 is super close to 200. So that's your first bar, 198. The 4 to 6 is 205. That's over. It's a little bit taller, just a little bit taller. This one. There you go. And your next bar is 22. So it's a really tiny bar. Less than 50, definitely less than 50. And that's it. That's your histogram. Crudely drawn, but if you had more space in a piece of paper and rulers and stuff, you can make this real nice. Shapes of distribution and graph skew. This is pretty easy, actually. And then we can see. We'll see. All right, so when you look at statistical data, there's many different ways data can be shaped, many different ways. And thus people can use the way the data is shaped to draw conclusions or make assumptions or predict forecast different things, predict different events. And usually this is based on what you see on a surface level, and you don't really include outliers or any other factors. It's just what you see on a graph. Usually that's what most people do. They'll do that stuff later. They'll look at the deeper stuff later, but for now, they'll just look at the graph and say like, okay, I'm gonna predict this is gonna happen. So first is the symmetrical shape of distribution. It makes the most normal and it's the most normal in quotes, and most sought after shape of the data distribution because it makes statisticians' lives easier when doing calculations like standard deviation or a chi-square test because it's normal. It's symmetrical, it's easy to calculate. There's nothing crazy going on. It's normal. It's also called the normal distribution, normal curve, or most commonly called the bell curve. This is the most common. It's called bell curve. Bell curve is the theoretical, if all your data is normal and collected well, without bias, without any outliers, any confounding factors, you probably get the bell curve, theoretically. Oh, whoops. That's what it's called, the bell curve. Well, actually, this is why it's called the bell curve. So this is what it looks like. So in a histogram format, it looks like this, right? So everything is like a mountain, like a nice hill, and they call it the bell curve because it's shaped like a bell out here. So if you did a histogram format, it just looked like the bars would look like this. If you made a line format, it would just look like this. And you can kind of see the mean is approximately equal to the median. And right in the center, the mean is equal to the mode, which is equal to the median in a normal curve or normal distribution or a bell curve. In the real world, you're not going to see this much unless the data truly is normally distributed or it's a miracle. But most of the time, you're probably not going to see anything this perfect. Maybe like this might be a little taller right here, or this might be like just non-existent at all, stuff like that. But this is the most sought after because this is the easiest to calculate with. Everything's in the center, everything is normal. So next two types of distribution is right-tailed and left-tailed. Oh, these are tails, by the way. So the ends are called tails. So the end of a histogram or the end of a graph. So if you had the normal curve, this part is like a tail right here. Notice how it looks like kind of like a tail, like in real life. This ending part is a tail. They call it tails. I don't know why. I never took stats, like I said. So you have right-tailed and left-tailed distribution. They call this because most of the data points or your frequencies are on the opposite side of its name. This might seem a little confusing, but it'll make sense later. And there's a low quantity on the side of its name. So low quantity of frequency on the side of its name. Like I said, it'll make more sense soon. So right-tailed means that most of the data is located on the left side, and there's a low amount of data on the right side that forms a tail, right? Because tail is like that diminishing part. It's this little smaller part because there's less and less data here compared to like something on the left side right here. Same thing, left-tailed, most of the data is located on the right side, and there's a low amount of data on the left that forms a tail. So left-tailed, right-tailed. So here you go. So left-tailed, so I'm gonna erase this. So notice that there's a tail right here on the left. There's a little tail. If I shade this in, that's a tail. And on the right, there's a little tail right here. It's called the right-tailed, left-tailed. But if you separate these two graphs, notice how most of the frequencies and the magnitude of frequencies is on the right side, and this one's on the left side for right-tailed distribution. So there's two ways to think about it. Either think the opposite or think the tail direction. I'll say that on the next slide. But yeah, this is what left-tailed looks like. This is what left-tailed usually looks like. This is what right-tailed usually looks like. So keep that in your mind a little bit, except it's all a lie. Because honestly, personally, I've never heard anyone call that left or right-tailed. No one says that. I've never heard anyone say that. I've never heard that before. Because we call it skewed left or skewed right. It's all a lie. Yes, left-tailed, right-tailed. I've never heard it like that. I heard skewed left or skewed right. It's the same concept. So skewed left means most of the data is on the right side and there's a tail to the left. Same thing as left-tailed distribution. And right-tailed or skewed right would mean that most of the data is on the left side and there's a tail to the right. I've never heard anyone say left or right tail distribution. I've heard skewed to the left, skewed to the right. That's it. And so when you're identifying if a graph is skewed left or right, there's two ways to think about it. One, like I said, think about the opposite of the name. So if most of the data is on the right side of a graph, then think the opposite and say it's skewed left. Likewise, if most of the data is on the left side, think skewed right. It also works for, this doesn't have to be histograms or like those line curves. It could be dot plots too, because if you had like a dot plot right here, like this, like that, this would be skewed to the right, skewed right, because there's a tail right here. And notice that everything is on the left. So this is skewed right, there's a tail on the right, everything is on the left. So you can think of either way. Think the opposite or think the tail. And a dot plot that looked like this, so like that, you would say skewed to the left because everything is on the right and there's a tail forming on the left. So it doesn't have to be histograms, it doesn't have to be those line charts. It could be dot plots, it could be bar graphs, it could be a lot of things, different distributions of data, different portrayals of data. Anyways, the second way to think about it is you think about where the tail is on the distribution graph. So if there's a tail on the left, then it's skewed to the left. So tails correspond to the name. If there's a tail on the right, then it's skewed to the right. Not too difficult, right? So like I said, if, whoops, almost done. But like I said, if there's a tail right here to the left and everything else is on the right, like so, skewed left because there's a tail right here. And likewise, if the tail to the right and everything, all your data points is on the left and it's skewed to the right. Now, if the dot plot looks something like this, this is considered technically normal distribution. Technically, if it is, it looks better if it looks like that because that's Berkshire. But this is technically normal as well because it's just even distribution. If it had something like this, that's approximately normal, but I'd say it's slightly skewed to the right because there's more on the left side. So it's just all up to your interpretation. Some people would say slightly normal, like approximately normal. Some people would say slightly skewed to the right. So just stuff to keep in mind. All right, so basically it's the same thing. Skewed left, because there's a tail right here on the left. And skewed right, because there's a tail on the right. Or you think about another way, everything is located on the right. So everything is more on the right than there is left. So skewed left, you think the opposite. And skewed right is more on the left. So you think the opposite and say it's skewed right. Two ways to think about it. All right, let's do some practice. Briefly summarize the distribution of each graph. Are they normal, skewed left or right, etc.? So I will give you guys a little bit. Figure this out. Is it skewed left, right, normal, or maybe something else? I don't know. So I'll give you guys a little bit. Yeah, I'd say that for number two. It's a little tough call, Zoe, but yeah, kinda. I said that in my answer. I do mention that. All right, so number one obviously is skewed left. There's a big tail, a really big tail on the left side because everything is looking on the right side. More stuff out here. And number two is some would say normal because it does look like the bell curve. Others would say since it's a little shifted to the right, the bell curve is shifted to the right. It has a bell curve shape, but since it's slightly shifted to the right, a lot of people would also say it's skewed left because there's a tail right here compared to the right tail. There are two tails in this one because they both fall off, but the left tail is definitely more noticeable. So hard call, but skewed left is also acceptable. So yeah, number one is skewed to the left. There's a big tail right here. And most of the data is on the right side, like I said. And number two is approximately normal distribution, or it's slightly skewed to the left. It's kind of a hard call. Personally, I'd say skewed to the left as well. But a lot of people, by glancing at it, they'd be like, oh, it's just normal. Look, it looks like a bell curve, right? But yeah. Okay. And these two are the last ones. And we'll talk, and we'll talk about tomorrow. I don't know. I don't have a PowerPoint ready for tomorrow. So I recommend you guys don't come tomorrow. But we'll see. Because I don't have like a Kahoot or anything ready. I could make one tonight, I guess. I've never made a Kahoot. All right, what do we get? Skewed right, skewed left? Yep. Basically, this is skewed right. You know, it's the tail right here. Skewed right. And this is skewed left because it's more on the right side. Now notice there is a tail on the right side, but the tail is much more bigger on the left side. So it's definitely skewed to the left. And this one's skewed to the right. So everything is comparatively more to the left, especially this big bar. Because if the center was right here, the big bar is definitely on the left side. Now scoot to the left, or scoot to the right, sorry, and then scoot to the left. That's it. You guys are done with your final lesson. Congratulations, guys. Hey. Yeah, like I said, if you come tomorrow, I'm not gonna have a lesson. I might not even have a PowerPoint. You are free to go. But yeah, I recommend you don't come tomorrow. But if you do, I don't know how I'm gonna entertain you for an hour. Maybe do like a small review or something. I don't know. But yeah, I mean, I'll be here tomorrow for the 1 hour, unless no one comes. If no one comes, then I'll just obviously end it. But yeah, you guys are done. There's no new lessons. That's the last lesson. Intro stats. I hope you guys learned something new. Honestly, most of the stuff I would have learned in like 4th and 3rd grade, maybe 5th grade too, instead of 6th grade. But yeah, I hope you guys learned something new, at least one thing. Like anything, not even math related, it could be anything. But yeah, I got nothing tomorrow. I'm gonna be honest. Is this the last lesson tomorrow? So today is the last lesson in terms of content, but technically tomorrow, like I have to have a class tomorrow, technically. I recommend you don't come tomorrow because you're not gonna learn anything, but I might do like a review or something. I don't know. I haven't made a PowerPoint for tomorrow. So technically today is the last lesson. And then tomorrow I'll still be here. But you're not gonna learn anything. You might just review, maybe. We'll see. I don't know. I don't know. So
Bye.
bye. Yeah, you're free to go.
Thank
Bye,
you.
Max.
Bye. Thank you.
So yeah, if like 1 or 2 of you guys come tomorrow, I guess I'll like find a way to entertain you guys. I don't know. But this is it. I'll see if I can email Cloud Classroom, say if we cut the lesson for tomorrow, or they'll probably tell me just to do a review. But I'll email them tonight because I really don't have a lesson tomorrow. And a review, I don't know if a review would even help for an hour. That's just, yeah. We'll see. But yeah, I recommend you don't come tomorrow. If you do come, which is totally fine because I'll still be here. Then I'll do something. I don't know. I'll find a way. So yeah. So if you have any questions, you could stick by. I will be happy to answer them. Or otherwise, you guys are free to go. So if you guys got anything, just tell me. Otherwise, I'll just end the meeting. Anyone? Anything? Anyone? Can you explain how to get average in percent and probability? Okay. Okay. Sure. I don't know what you necessarily mean by that, but let me see. Let's go. Give me a second. Hold on. Okay. So what do you mean by that? Necessarily, let's see. Oh no, it's doing it again. No, okay. Hold on. Okay. Oh, it's doing it again. Okay, that's okay. Hold on, give me, I don't know why it always does this every time. Okay, how to get average in fraction and turn into percent? Well, you can only get average from multiple numbers. Well, okay. Because, yeah, there's no point. Because if you say like, oh, whoops. Come on. Okay. Like if it's the average of like a fraction like 3/7, the average of that is 3/7 because there's only one number. So I don't know what you mean by like taking average and putting a percent. How to get average fraction to turn to percent? I know how to. I'll tell you like how to turn a fraction to a percent, just straight up. But like, there's no average involved. Average is only involved in lists of data. Keyword is a list. You have to have multiple units, not multiple units, multiple numbers, multiple things to find the average. Like I could say I can find the average of 3/7 and 5/8. I can find the average of these two numbers, right? Because I'd just be like 3/7 plus 5/8 all divided by 2. I can do that. Like the 3/7 is average. And can you explain how to turn 3/7? Oh, okay. So turn a fraction to percent. Okay. Well, the easiest, simplest, most straightforward way. So if your probability was a 3 and 7, so like let's say you had like 7. Whoops. Hold on. Okay, let's say you had 1, 2, 3, 4, 5, 6, 7. Okay, let's say you had 7 marbles, I guess, or 7 balls or whatever. Change to black. So you have 7 balls, and the probability of picking a red ball is 3/7. So you're trying to see how to turn this into percentages? Turn this into percent? Yes, okay. Well, the most straightforward way is remember the formal definition. The definition of a fraction is just the denominator, in dividing into the numerator. So in other words, it means 3 divided by 7. All right, so remember that. So the most straightforward way to find a percentage from a fraction is you just simply divide this out. You simply do the operation. So you have this. So because 7 can't go into 3 because 3 is too small, you have to add a decimal point and add a 0. Now 7 can go into 30. For example, this one would be 4 times. So 28. And then you just keep bringing zeros down. Simple division. 7 can go into 20. 2 times, so 7 times 2 is 14. And you just keep going. This is probably gonna be an infinite decimal. So I'm going to 67 times? 8 times? Yeah, 8 times. 56. And you just keep going. Dot, dot, dot. So just keep going. Oh, whoops. So yeah, the most straightforward, simplest way is you just divide out the number. So for example, 0.428, then you take your 0.428 and you multiply it by 100. So first you want to divide out the fraction to get a decimal and then multiply it by 100 because remember, definition of a percent is per 100. And in this case, this would be 0.428 times 100. So just simply move this over and you have a 42.8% chance from 3/7. So that's how you find a percent on any fraction in general. You just do the operation. So do 7 or 3 divided by 7, because this bar means divided by in the fraction. And then you just multiply it by 100, or you move the decimal place 2 times. Sorry. I hope that cleared it up. Let's try something else. Try a different fraction. Let's see. Give me a fraction. Give me a fraction. 5/8? Okay. So you have 5/8. And so you have like, I don't know, let's say you had 5 squares and 3 circles. So probability of getting a square is 5/8 because it's 5 squares out of 8 total shapes. Remember, it's a ratio of the chances for and total chances. 5/8. Remember, 5 divided by 8. This bar means divided by. So 5 divided by 8. So same thing. You just simply do the division. If I did 8 divided by 5, that would look like this, by the way. It looked like that. Sorry, my voice is getting raspy. So 5 divided by 8, and you just simply do out the division. So 8 cannot go into 5 because 5 is too small. Add a 0 at the decimal point. 8 can go into 50. Let me think. 4 is 5. 5 times? No, 6 times. So 48. Bring down the 0 again. 8 can go into 22 times. 16. And you just keep going and going. 8 can go into 40. 4 times? 3 times. Sorry, 4 times. Or 5 times. Yeah, 5. Never mind. 5. And so your decimal, 5/8. So 5/8 in decimal form, as a decimal, is 0.625. Now, as a percent, you take your decimal and you multiply it by 100, or in other words, you move the decimal place 2 places over. Decimal point 2 places over. So it'd be 62.5%. So a 5/8 probability is equal to a 62.5% chance. Or 5/8 in general is equal to 62.5%. Like a percent. 1.6? 160? Where are you getting 160 from? 1.6? Oh, I see. Yeah, if you had a 1.6 as a decimal and you make it a percent, it'd be 160%. Yes, over 100% exists in the real world. Anything else? You want to keep going another one, or you have any other question? You can give me another fraction if you'd like. Just if you want to clarify. Or if you're clear on this, then yeah. Got nothing? I'll do a little quick trick. So obviously everybody knows the Can you explain the Pythagorean theorem again? Oh man. Okay. So if you had a right triangle, right? If you had a right triangle This is a right triangle, a rough estimate. Don't worry about this part. If you had a right triangle with side A, side B, and side C, Pythagorean theorem says that the square of this little side first, a squared, plus the square of this side first, b squared, the sum of these two sides squared is equal to this hypotenuse. Remember, this is called the hypotenuse, the diagonal, is equal to the hypotenuse squared. That's the Pythagorean theorem, made by Greek mathematician Pythagoras. That's why it's called Pythagorean theorem. Pythagorean. I assume you're talking about the Pythagorean theorem based on your spelling. Can you spell? Pythagorean. And a lot of people will have like little visual proofs. So if you had like A, if it was squared out like that, like literally made squares, and then this was squared out, like actually made to literal squares, it would equal this if it was extended out and made to literal squares. I've seen visual proofs like that. Personally, I don't know. I mean, this is true, by the way. This theorem is true. I don't know the proofs exactly, like how did they prove it, or how did Pythagoras prove it, but I do know it's true. It is 100% true. It's a theorem. So if you had leg A, leg B, these are called legs, this one and this one. If you had leg A and leg B, the sum of both legs squared is equal to the hypotenuse squared. That's basically what I'm saying. A squared plus B squared equals C squared. If you had A, B, and C. I mean, at least you're not learning anything like the law of sines or something. If you had the law of sines is this is like a regular triangle, whatever, like your typical, the triangles you see in most places. Law of sines, if you had A, B, C, angle A, angle B, and angle C. I think the law of sines is like A over angle A is equal to B over angle B, which is equal to C over angle C. Something like that. How do the people get the squares? I'm talking about the visual proof because I don't know personally. I just know this exists. I don't know the exact details. People have proved it. I'm just saying like they're proving the Pythagorean theorem. But I don't know like on the right triangle, the visual proof. Yeah, I don't know. You have to look it up. Something. Let me look it up real quick. Right there. Visual proof. It's probably best if you look it up, but because it requires like squares and whatnot, I think. Okay, so let me see. Okay, so the best proof I have, so have your square. So this is A squared. This is B squared. C squared. And imagine like a coordinate grid. There's a coordinate grid right here. So your y-axis, x-axis. And let's see. And basically, if you put the c squared and you make it straight, like so, c squared, it would look massive, right, compared to a squared, b squared, because it's obviously the biggest side. And the visual proof says that no matter what side length of a and b, it always equals c squared if you square it out, make these squares. So something like a squared plus the size of b squared would always equal c squared. But how do they get the squares on the sides of the right? Oh, they just make it. That's how you prove stuff. You just make a lot of stuff. You just draw it out. You make it. That's how you get a lot of proofs. Be like, okay, say if I made this giant square that has the side length of square. So notice how, remember properties of square, right? So square means all sides are equal. So they just said, okay, let's just draw it out. Let's just take this right triangle, draw the right triangle first, and just draw out the square. Mathematician would be like, okay, let's just draw out the square. And so this is side length C, this is side length C, this is side length C, this is side length C. That's what a square is, remember? All four sides are the same. So C, 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 C. And they just draw it out. They say, okay, let's attach it to the right triangle. And now let's make a square with side length B, 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 B. And this is A, 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 A. And they see like, hey, this side length and this side length probably make up the side length A plus B. The side length of A plus B probably equals C, side length. And thus, if you make the square out, because you have to square it, because that's the area of a square, thus the area of it is equal to C squared. Something like that. Don't quote me on that. Don't remember. I recommend you look it up yourself on YouTube. Look up proof for Pythagorean theorem. So write this down. Proof for Pythagorean theorem. I don't know if you live in the US. Is YouTube allowed at where you live? I hope it is. Because I would recommend you look it up on YouTube. YouTube has hundreds of videos on this because it's such a memorable theorem. It's such a clean, well said, well created theorem. There's nothing fancy about it. There's nothing difficult about it. It's just clear cut. Everything is simple. So if you have YouTube, I don't know, do you have YouTube at where you live? Yes or no, Zoe? Yes. Okay. Yeah. So I look this up on YouTube. Proof for Pythagorean theorem. And you'll probably get here. I'll even give you a link. Let me look it up. Let me look one up myself. Khan Academy is perfect. Okay, here we go. Okay, I will link this one out. This is a good one, really good one. TED Talk, definitely. So these two are pretty good. These two are really good YouTube links. Yeah, but Pythagorean theorem, ladies and gentlemen. That's I know there's other people here. You guys can go, guys. Mani and Gloria, you guys can go if you want. You guys don't have to stay. Only Zoe has a question. So. So yeah, I recommend if you have any other questions, I guess you can ask me right now. But I recommend you look at those two videos if you're that interested, and you probably learn something, a thing or two, and see why Pythagorean theorems is correct. Pythagoreus's, his name is Pythagoras, why his theorem actually works for right triangles. Remember, this only applies to right triangles, so only right triangles. But if you have any other questions, feel free to ask me in the next couple minutes or so. Otherwise, I will end the meeting, and maybe see you guys tomorrow. I recommend you guys don't come tomorrow, but we'll see. I mean, I'll still be here tomorrow. Okay, I'm gonna assume. So is the median the same as the average? No. The mean is the same as the average. MEAN. I'll go back. The mean. So remember, the mean, also known as the average, is the sum of all your data divided by the n amount of data you have. So the mean is the same as the average, not the median. Median is its own thing. The mean and average, so mean equals average. There you go. Anything else? Oh, there you go. That's my yawn. Ooh. I wasn't lying when I said I was tired. Any other questions? I'll give you a couple more minutes, but otherwise I'll end it soon because I have to go as well. So yeah, if you have any other questions, just throw them at me. I'll see if I answer them real quick. What is chi-squared? I don't want to answer that one. That's a question I can't answer in like 5 minutes. Okay. I won't tell you how to get the result of it. So chi-squared, it's called a chi-squared test. It comes from the that's a good question though. Yeah, I did mention that. It comes from the Greek symbol of chi, which looks like X, but with this little fancy part, so it's like that. Chi. CHI. It's called CHI. Here, if you want to look it up yourself, it's chi squared test. But I can't answer it. Well, okay, I'll tell you. I won't tell you how to get the result of a chi-square test. But it look like that. Chi-square test is in stats. It's a way to see if your data is or isn't statistically significant, aka your p-value, or using a different p-value, using a certain p-value, see if your data is statistically significant or not. I believe something like that. Now, what does that mean? Okay, so you probably don't know what that means. So a p-value in stats shows that if your data is statistically significant, and what that means is that is your data really actually random? Is it because when you do a statistical project, a project with stats, your data has to be random and fair. You don't want to be biased. You don't want to make up your data, and you want to make sure your data isn't due to like chance or due to coincidence. And not chance as in probability, as in like just a really, really good coincidence that like, say you survey 50 people and they all say they like vanilla versus chocolate, and you're like, okay, are you sure you? And when you think about it, when you take the results of that, you have to think to yourself, did you randomly interview the people, ask them, do you like vanilla or chocolate? Because if you ask 50 people and they all like vanilla, obviously your data is bad because you already know they like vanilla, so they're going to say they like vanilla. So chi-square test, a p-value, shows if your data is statistically significant, if it actually means anything, or if it's due by chance. If the p-value is small, then it actually means something, I believe. If the p-value is large, then it's probably by chance, and your experiment probably sucks. I'm not gonna lie, sorry. It doesn't suck, but your experiment is probably flawed in some way, or something bad just happened, or it's due by chance. Now, I'm sorry if I'm going a little fast, but it's a lot to explain, I know. Now, a chi-square test, it takes whatever p-value you think you want, and usually it's gonna be a small p-value. It takes your p-value, And what it does, it's when you do like a science experiment, you have a hypothesis and a null hypothesis. The null hypothesis says what I think is going to happen is not going to happen, and it's probably not by chance. I believe that's one null hypothesis. And then a regular hypothesis is like this is going to happen, and it's going to happen no matter what. That's your hypothesis. But the null hypothesis is like, okay, nothing I did in this experiment mattered, and then whatever I hypothesized originally didn't even happen, and it's not by chance, just nothing happened. That's a null hypothesis. And a chi-square test, based on whatever value you get for your chi-squared value, determines if the null hypothesis is rejected or accepted. I believe if the chi-squared is larger than a certain value based on your p-value, then the null hypothesis must be accepted, and your experiment is your original hypothesis is rejected. So basically everything did happen by chance, or something was flawed, or your experiment means nothing. Not nothing, but like it doesn't mean much in terms of stats. But if your chi-squared is small, chi-square test is small, then your experiment probably did mean something, and you can reject your null hypothesis, and whatever your original hypothesis is, you can probably accept it. And so your experiment probably does mean something, and it means something that's not due to chance as well, probably. So yeah, I know that was a lot, and that was kind of poorly explained because, like I said, I never took stats class, but I know how to do it because I've done it before for science, and I've done it to help my friends, and my friends asked me to help them when I told them I didn't know how to do it, and they're like, okay, then help me do it, or you just learn on the fly. So I just learned on the fly. I learned really fast about this kind of stuff, but very surface level. And so this is like a summarization of what I knew. I learned on the fly. Like I learned super duper fast. Like nothing in depth. I didn't read any books. I just went online, looked this up, looked that up, and this is what I got. So yeah, that's very long. You probably didn't understand much of it, but just know chi-squared is to see if your null hypothesis is able to be rejected or accepted. And a null hypothesis, like I said, is anything that is not due to chance, and your original hypothesis doesn't matter. It's good question though, I guess, because I did mention it. Yeah, that's a good question. And yeah, thank you for that question, because you got me talking about it, because I had some good times talking to my friends about this when they needed help on their homework. And they told me to learn on the fly. I was like, Kevin, you just got to learn it right now. I'm like, okay, sure, whatever. I got time on my hands. So I just learned it real fast. So yeah, any other questions? Otherwise, I will end it at 6:30 or wherever you live at the 30-minute mark, because we have 3 minutes in 3 minutes. So if any other questions, you tell them right now. And don't be shy. You know, there's nothing. I mean, I love answering your questions. It's pretty good. Pretty decent. So my voice is probably dying right now. I don't know if you can see it, but yeah. Any other questions? Yeah, you got 2 minutes to ask a question. Right now I'm just relaxing. See if you have a question. Is this the last class? Yes, in terms of content, but there is technically another Zoom meeting tomorrow. I will be here, but you don't have to join tomorrow, I guess, because I'm not going to teach you anything new. I might be like a review or something. We'll see, but this is the last class, yes. The last lesson, rather. I knew you were going to ask that. You can go, Manya. You're free to go. You've been, as always, just asking questions. I'm answering them. Deviation, standard deviation. I knew you were going to ask that. All right, standard deviation. It's a formula. All right, so standard deviation is this symbol. It's called like the omega symbol, but this is like a lowercase because this is like, that's ohms, sorry. The uppercase omega is something else, but it looks like this, like an O with the line on top. Or we call it S dot D, SD, standard. So standard, I'll spell it, standard deviation. I believe I spelled that right. Sorry, this is an O. That's an O. Standard deviation. SD, we got SD, that's a D. Standard deviation in the simplest terms is the average distance away from the average. I don't know if you caught that, but what I mean by that is like, let's say you had 1, 2, 3, 4, 5, right? And the average of this would be 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2, 1 plus 2 plus 3, 4 plus 4 plus 5. 15 divided by 5 is 3. So the average is 3, right? Sorry. The average is 3. And so the standard deviation is the average distance away from the average. Each number is away from the average. So what I mean by that is like 1 is 2 away from 3. The average is 3. So 1 is 2 away. 2 is 1 away. 3 is 0 away. 4 is 1 away. And 5 is 2 away. So the average distance from the average is 2 plus 1 plus 0 plus 1 plus 2 divided by 5. And so you would get 6 fifths, which is approximately 1.2. It's not approximate, 1.2. So the 1.2 is your standard deviation, or SC. And so this means that each number is on average 1.2 away from the average. So in this list, each number, 1, 2, 3, 4, 5, has an average of 3 from this list, is the average of 3. And each number is 1.2, on average, 1.2 away from the average of 3. So that's standard deviation. And there's an entire formula on it. My calendar says it's 2 classes next week. Yeah. Next week, tomorrow there's a class. Sort of, not really. But I'm not going to teach you anything now. I'll see. You don't have to come tomorrow, in my opinion. I recommend you don't. But I'll see how if you guys do come, I'll be here tomorrow. If you guys do come, I'll find a way to do something. I don't know. Okay. So yeah, I hope that cleared it up. It's the average from the average. There's an entire formula on how to get it. It's long, it's big, it's fancy. Friend. So there's a formula on how to do it. I'll tell you what it means. I'll actually tell you like right now because I know what it means. I'll tell you. So this standard deviation is the square root of the sum of all your numbers in the list. So if you have 1, 2, 3, 4, 5, I'll tell you how to apply it. It's the square root of the sum. This is sigma. Sigma means sum. Is the square root of, this is the last question, by the way. It's the square root of the sum of all your numbers by the, of the quantity of all the numbers in your list minus mu. This is mu, by the way. It looks like an M. It looks like an M right there, mu. Minus mu. Mu is your average. So it's the sum, it's all your numbers minus the average squared. And the reason why they do that is because we don't want negatives. So remember, the average of this is 3, right? And technically, 1 is 2 away from 3, but 5 is negative 2 away from 3. And so that's why we square it, to get rid of this negative right here, right? Or, yeah, see, because, yeah. But in reality, it's actually 1 minus 3 squared, the first one, plus 2 minus 3 squared, right? Because these two are negative. Anyways, divided by the number of elements you have. So there's 1, 2, 3, 4, 5 elements, 5 different numbers. It's kind of like average. That's what the entire equation means. Yeah, this is sigma. It's not E, it's a sigma. Sigma. It's a Greek letter, S-I-G-M-A. Sigma. It means the sum. It means the sum. So let's apply it. So let's say if we want to find the standard deviation of the list 1, 2, 3, 4, 5, I'll prove to you that it is 1.2. So standard deviation equals the square root of everything divided by 5, because there's 5 different elements. The sum, so you're adding here, of your numbers, if each number minus the average squared. So 1 minus 3 squared. So you move on. So you finish with 1, you move on, go 2 plus, because it's a sum, 2 minus 3 squared. You're done with 2, keep going, move on, plus 3 minus 3 squared, plus 4 minus 3 squared. I'm going to erase the sigma. I hope you caught that. So I'll rewrite it, don't worry. So sigma, remember it's a sum, plus 5 minus 3 squared. So it's a square root of all that. So let's calculate this out. 1 minus 3 is negative 2. So actually, I'll tell you. So 3 minus 3 is 0. So this goes away because 0 squared is 0. 0 times 0 is 0. 1 minus 3 is negative 2. So you get negative 2 squared plus 2 minus 3 is negative 1. Negative 1 squared. 4 minus 3 is positive 1. So plus 1 squared. 5 minus 3 is positive 2. So plus 2 squared. Notice how they mirror each other? That's because the data is set up really well. But in real life, it probably won't. So then you simplify this. Negative 2 squared is negative 2 times negative 2. Now, there's a little, if I had negative 2 squared, that equals negative 4. But if I had negative 2 in the parentheses squared, that equals negative 2 times negative 2. And as you know, a negative times a negative is a positive, right? So negative 2 times negative 2 is positive 4. So in this case, positive 4 is right here. So if you keep going, that's a 5 right here. Pretend that's a 5 on the bottom. I'm running out of room. So negative 2 squared is 4. Plus negative 1 squared is positive 1. Plus 1 squared is 1. Plus 4. Right? And I think I did it wrong. Anyways, so no, I did it right, sorry, but I did the original part wrong. So then you just add it all up. So 4 plus 1 is 5, plus 1 is 6, plus 4 is 10. So square root of 10, square root of 10 over 5, which is equal to square root of 2. So your standard deviation is equal to square root of 2, which is approximately, I believe 1.2. 1.4 actually. 1.4. Approximately 1.4. So in total, the standard deviation of this list, I'll rewrite it. 1, 2, 3, 4, 5. The standard deviation is equal to the square root of 2, or approximately 1.4. Which means the average distance from the average in this list is 1.4. So yeah, I'll rerun it. Let me erase this part. So let me relabel everything. So this is equal to standard deviation, the O thingy, it's called omega. Xi or x1, xi, this is I, is equal to basically your elements of your list, of whatever like contents of your list. So this is xi1, xi2, xi3, xi4, xi5. Mu, this thing called mu, it's called mu. I don't know how to spell it because the technically it's spelled like this. It's called mu. Mu, it's spelled mu. Look up Greek symbol mu is equal to mu. Notice how it looks kind of like the M here. It looks kind of like the U as well, but it's called mu. So mu is equal to your average, and n is equal to amount of elements you have. My handwriting is horrible. Amount of elements. And my voice is dying. Oh my god. I haven't talked this much in a long time. So yeah, that is standard deviation in a nutshell. It's the square root of the sum of each element in the list minus the average, quantity of each element in the list minus the average, squared, divided by the amount of elements you have in your list. That is the definition of standard deviation. The formula, sorry, this is a formula for standard deviation. I'm not gonna ask for any other questions. We're 40 minutes over time, but I mean, those are good questions. Yeah, no problem. I'll look, if you, like I said, if you want to look it up yourself, I'll spell it out. Standard deviation. And you have chi-squared. Chi-squared. This is two words, by the way. Chi-squared is a hyphen. It's chi-squared test. Yeah. And you're not going to use this until like 8th grade, 9th grade math, or I don't know, secondary. How's it work? Tertiary school? Either tertiary, because in America we have elementary school, primary school, middle school, or secondary school. Oh yeah, secondary. You're not going to use this until secondary school, like late secondary, like mid-late secondary school. A standard deviation. Chi-square class, you're not even going to use until late secondary school, because chi-square test is actually a stats-focused class. That's where you learn it. And stats is amazing. Like I said, I personally think that they should teach stats more, because stats is very relevant in a job. Like if you want a job as like a scientist or like a banker, not a banker, like a, not banker necessarily, but like a financial advisor or anything like that, anything finances, stats is important. A biologist, biology uses lots of stats. Biology, the study of life, plants, life, all that stuff. Biology uses a lot of stats, because when they do experiments, they want to see life experiments. They want to say, hey, if I give a so-and-so like a fertilizer to a plant, is it going to grow out well? And I'm going to take the stats for it, say like plant height, see how much it grows, and say, is the fertilizer good or not? Is it due by chance? Is it due by chance or not due by chance? What's the chi-squared of it? What's the p-value? Psychology uses stats a lot. Psychology is a way to measure the effectiveness of their psychological experiments. Like say they want to see like, what's a psychological experiment that could be important? Like see how many times people yawn a day, and they measure how many times people yawn a day based on how much sleep they get and how it affects your brain chemistry and the psychology of it. You would use stats for it, because maybe some people just yawn like me. I yawn for no reason. Even if I'm not tired, I just yawn. So yeah, so stats is important, in my opinion. They should teach it more. But yeah, I'm going to end the class on that note. If you're interested in stats ever, stats is it's a hard field. I'll give you that. Stats is pretty hard. Actually, all math is, all higher level math, everything is hard. If you have to put the hard work into it. If you are ever interested in stats, I do definitely recommend you go for it, because it's a good field of study. And if you're not interested, then obviously don't pursue it. But like stats is very time consuming. Stats is not hard, but it's just very time consuming, mind boggling. You saw, remember the standard deviation formula, you just saw how long it took just for 5 different numbers. Imagine if you had to study for like 200 different numbers or 200 different things. It'd take a lot. So that's why we have calculators today and computers to do that kind of stuff. But back then, we didn't have that. So yeah, stats, very interesting. So I hope you I guess enjoyed that little talk, little spiel about stats. But I'm gonna end the meeting. I hope you guys I hope you enjoyed that, Zoe. I don't know if I'm gonna I really don't know what to do for tomorrow. It's just gonna be like a review or something. I don't know. If you come tomorrow, I'll still be here. But if you come tomorrow, I really don't have a lesson. So, on that note, I have to go eat dinner. Hope you guys have a good rest of your day, night, afternoon, whatever. And I will see you guys tomorrow. Maybe see you guys tomorrow. Maybe. Have a good one, guys. Bye bye.